正在录制此会议。
So let's begin our class again. And I think since it is the last lecture class this week, and we will have the final next week, right? So Bill is still announced. First, the final will be still closed book, and please bring your calculator with you. And I think there will be still 3 hours for your final. And maybe I think of it.
正在录制此会议。
Okay, well, the small thing now, right? First, we talked about the how much current we can amplify, and then we multiply with the loading, and then from the input side, we try to use the voltage divider. So how much signal we can take from the resistance. So you can think that if you are working with a really high resistance at the gate pole, that would be a good thing for you because if you look at this function, if you want to pass your signal well into VGS, you need to mention the RG should be really large, right? So it is a good benefit for you. So if you build RG, the resistance in the function generator can be ignored. And then we can determine how do we amplify this one. So the resistance in parallel is determined by the lowest resistance. So depend on RD or IL because RO is typically large. For RD, it is used to support your voltage. So the RD is on the order of kill ohm. So the question is, what is the load impedance? So that it also explains why sometimes we see on SA, earplugs type SA. What happened here is the load impedance is 5 ohm. So when you connect to 5 ohm with stable kill ohm, it's mostly dominated by 5 ohm. So what happened here, even so we get a GM, maybe 2 to 3 milliamp per volt, or even with BJT, 40 milliamp per volt, you multiply with VGS, it seems the signals doesn't really amplify. The reason is because your resistance is too low. Okay, so there will be an additional way to go. And if you are interested, you go back to look at the electronics textbook on the graduate level. So you can look at, hey, what is the application? So here's one example. So you can think that you have 1 millivolt as the input. What we get here is the frequency response. So we get a output at around 2 millivolt. It means that maybe you double the frequency, but not much. Maybe you will also notice there will be a drop down or rollover at the low frequency. Please remember this one is not the VDS over VD. It is the frequency over the output voltage. So why we have this rollover? The reason is because we get a capacitance around your transistor. So if you look back to the capacitance we use, there will be still at least 2 capacitance at the input and the output pole. So if you want to increase your low frequency response, typically you use a large capacitance in order to push the low frequency response down further. So that's the reason maybe I'm not sure how many people use bass when you watch TV or hear the music. The bass means that typically there's a large capacitance required. So typically if you work with bass, the system is large. You need to use a large capacitor. And how about high frequency response? I think most of you design fancy resistance. In PSpice, they even give you really high frequency response, so you can see the response seems to be a constant. But if you are working with the practical device, we work with several gigahertz transistor. So what happens here is there will be another roll down. So this roll down is induced by the capacitance in the resistance in the transistor, not from the circuit. Okay. And why there's the capacitor in the transistor, that speaks about the device. Okay. Yeah, quickly show the next slide. What we get here is that we add an FR resistance in the source side. So what happened here is you can see the amplification can be slightly I don't want to cover that part, so you can think that if you get additional RS, the resistance at the source side, what happens here is you lower your amplification. Okay, the reason is because it divided by extra 1.3 RS. So if you're interested, you can go back to the previous uh, equation. You can see there will be a divider of 1 plus 3 RS. But the part we want to do is because we want to increase the frequency response. So we want to have the CPU get better frequency, uh, better performance at a high frequency. So the question is why we have this high frequency response and how do we improve it? So you can see if there is a capacitor, we need to charge up, and then we need to deplete the charge in order to turn off your transistor. And during this period, the delay times will be proportional to RC. If your resistance is larger, you get a slower response. If your capacitance is larger, you get a slower response. For the transistor, how do we avoid or increase the response? So what is the transistor? Okay, maybe I just use this picture. That's nice. So we connect different voltage. So here's the drain gate source side. And as long as we have the charge separation, we have different voltage, there will be a capacitance. Okay. So how do we work on this? So the first thing is that okay, so we get a GS as a charge difference because we get dielectric here. So we have certain accumulation charge, positive charge on the surface of metal, negative charge along the channel. Okay. So it seems there will be a capacitance. So you can see, okay, so when you charge up and deplete the charge, you get a certain capacitance between. Okay, so that will slow down your response. And what is the capacitance here? So you can say the CGX, we can denote it by A, and then here is the slow side. So there will be a capacitance from the CGS. Okay. And then how much degree of this CGS? It is a dielectric which is separated by oxide. So for this oxide capacitance, typically you notice the area divided by the separation distance. So you can think that the capacitance will be something like what is the area here? The area is the maybe I draw it with a three-dimensional space. Okay, so you know here is the unit capacitance oxide. And here's we have a plate. So the capacitance is the area divided by L, but the L is denoted by here. So I use different wording, maybe divided by T. So C outside is epsilon outside over T outside. Okay, so it is the thickness of the outside layer. And then what is the area? So we need to multiply with the area. It is the unit capacitance. So the area is here, we denote it by W, and then we know it is channel length L. So we just consider the help side, the gate to source side. So we can see that with this side, we get the only help L multiplied with W multiplied with CS. So we get this capacitance like this. Okay, and then if you consider there's another capacitance which is the drain capacitance, we can say if it is in inversion, so we just first consider it's inversion without applying additional drain voltage. So your charge will be uniform along the channel. Okay, so let's just consider we get a negative charge here, we get a positive charge here, without applying VDS along the channel. So CGD will equals to CGS equals to 1 over 2 LW dioxide. Okay. And then in the situations, you can consider, okay, I get additional drain induced charge distribution in which we get more charge along the source side. This then there will be discharge in the drain side. So what happened here is there will be redistributed this behavior. So there will be CGS, which is around 2 times the outside. And the CGD, since there will be this charge here, so you can see there will be no, since we say the voltage could be the same, because we pinch off the channel, the voltage is high, similar to VGS. Under this constant, since there's no voltage difference, we get a zero charge. So you can say almost zero, or you can say it is pinch off. Okay, so under this constant, the question is how do we judge additional capacitance? Not only is the capacitance appeared here because we already defined your outside capacitance, and there will be a trade-off. If you replace your material with high-K, even we increase the current, but there will be a penalty in the frequency response. So it seems to be a benefit. And how about the other one? Where's the charge we have? That will be a really small portion of the capacitance we may have. So you can imagine how do we connect this wire? So typically you have the metal gate, FB. So you have the drain. Sorry. So you can see it is the metal plate or metal wire connect to your source and the drain side used to drive your voltage. And then here is the gate one. So you can see here we have 3 different wire bound down to your substrate, down to your source, drain, and the gate. And then next, when you apply the voltage to this metal, there will be a spacing in between. There will be a outside dielectric, typically using outside. So there will be additional capacitance, but it is really hard to calculate because you get the style of your MOSFET with different FD connection. So the spacing is random, but you can still consider how do we evaluate the capacitance. If you get the separation between these connection narrow, you get large capacitance. Because the capacitance is determined by the area divided by the spacing between metal or between different voltage. If you get a smaller spacing, like a really fancy technology, 3 nanometers, 5 nanometer technology, what happened here is the spacing between two connections is really narrow, get a large capacity. And of course, if you further increase the height of this connection, typically there will be several hundred nanometer or several. Typically, I think it is around 17 to 19 nanometer for the first empty connection. I'm not talking about the metal wire about, but it is first layer to the metal gate, drain, and the source. It is lengthy. So typically we use copper, yeah, so typically we use copper. So for these connections, you can say if you get the higher of this FD, you get the lower one. If you get this spacing between metal connection smaller, you get a higher capacitance. And how do we improve it? Because we want to shrink the dimension, always we put this metal connection closer with each other, as long as they are still isolated by certain dielectric material. And how do we improve the capacitance? And then this area will be the dominant part. Because I think you can say here, of course, we get certain capacitance, but this one will be maybe a small portion. The other ones will be a large portion because the area will be much larger than this part. Okay, but if you are working with just the area here, that's the reasons why maybe you work with 700 megahertz, you still see a really constant performance. If X-Spice is still going to show you the high frequency response, but you need to consider the entire connection, entire integration. And for this integration, how do we improve the frequency response in some technology? So I think maybe you work with CPU, sometimes the operation frequency is around 4 gigahertz. That will already be the same frequency back to 10 years ago. So now transistor seems to reach a limit. We cannot give it further response, further higher frequency. Okay. And then there will be a lot of ways, like how do we improve the frequency response. Since we talked about it later, as long as it to separate your voltage, you can use it. So, like in 3 nanometer technology, TSMC, they have certain way to reduce the capacitance here. So, what things we can do? The TR size seems to be not this one. So you can think there will be capacitance between metals, maybe C and D. What is the capacitance here? It will be proportional to the area epsilon over distance. Okay, the distance is determined because your dimension, your density of chip is determined. So the smaller is good for your density, but it's bad for capacitance. But you cannot relax it. No one want to make your chip bigger, right? Area, again, if you get a higher density uh, transistor, you always have a really high density of your FD or connection, a lot of connection within the same area. That will increase your area. Okay, both give you better side effect. What else we can do? Excellent. Okay, so people work with the low pattern field. So the reason is because they want to boost up your frequency response. So maybe you heard about high K, you heard about low K. You know what we want to study here. For high K material, probably we use it as the gate material in which we want to boost up the current. For low K material, we want to replace the surrounding insulator or the conventional way we use IOD outside. But here we want to replace with certain low K material. What is the lowest gate we can get? What is epsilon? Lowest epsilon we can get? 1, right? That's exactly. Right? So what is the, we build up a dimension as 1? It's like the air, right? Yes, they are working. So how do we form it? So the idea is that in empty formation, we try to use a different way. Like here is the metal gate. Maybe I try to draw here. By the way, work with big plate. I try to draw it random. So you can see here is empty. So we get 3 combination. Here's empty, filled with metal. And then here is those thread. Here's the gate. Here's just moistness. And the letters they previously used ammonia as a downstream fuel. And then they use the ammonia, remove the ammonia, remove the ammonium. So you get certain air hole. And what they happen here, of course, you want to build up the architecture, there will be a lot of metal connection involved. So they use a really low coverage ratio material like a sparkling technology. So they just try to artificially build up a film in which there will be no building capability because the hole is too narrow, like just a few millimeter. So when you are doing a fabrication, you do not use the ALD, you do not use the atomic layer deposition, use sparkling, CVD, or any kind of fabrication technology. It will automatically form a hole for you. It is a good thing, but sometimes people working in fabrication, they say it is bad. It's just like a defect. But the question is how do you control the hole dimension? You need to make sure every hole are similar. Otherwise, there will be some performance variation. Okay, and then what I did later is like maybe almost 10 years ago, like in 2018. I think this idea is not a new idea. Like Intel is working on that. So we purchased some Intel CPU, do the DEN, force it, and then finally there will be some hole in between the transistor. So you can consider how do we make the transistor improve, not only to shrink the dimension, you can consider replacing the material like a high K, low K, or even air hole, or we call it air gear. So you are able to build up a really fancy transistor with high performance. Okay, so that is the power for semiconductor technology because you know the process, you know the boring equation, but as long as you know the equation, you can try to improve it. That is the main idea. Okay. We already covered this. Okay, I think this one is mostly in circuits and how do we improve the circuit performance. I don't want to cover that much. So here's the high-frequency response as I mentioned. So you can think not only from the transistor itself, there will be a voltage separation between the outside layer. So you can see there will be a CGS, CGD. So you can see the conventional circuit, we didn't have these two parts. So as long as the AC is not high enough, we didn't look at the capacitance. But if you work with high frequency, you get an extra CGD and the CGS as I mentioned here. Maybe you can say, okay, so maybe GD is not so important because the voltage may not be significant, but you still need to consider. I will talk about why. So you can think that in trial region, so we get the in trial region, we get the same error distribution, CGD equals to CGS. But if you are working with saturation regimes, the CGS will be more significant, and also we get additional overlay capacitance. So what is overlay capacitance? Just like we only consider capacitance here, but your metal connection at the source side is not precisely at the edge, right? So there will be an overlay in between. So that's what we call the overlay here. Okay, so the overlay here is still outside. Okay, so there will be some overlay capacitance. And also, if you are able to replace the outside here with local material, that's still a good thing. But because this overlay outside will not impact your current, right? Because this one, the current is determined by the metal gate here, as we previously mentioned. We only had the charge dispersion by the metal gate, not by without metal gate. Okay, so once we get the high currents, we can replace the overlay. So also we try to reduce the capacitance with the air hole with the overlay capacitance. And then we can see that based on this equation, the CGD also has the overlay. Even CGD is 0 at the saturation and the pitch region, but there will be an overlay between the drain side and the gate side. So the MD will not place immediately after the gate side. So they will get a certain overlay separation. I think in 5 nanometer technology, it could be like a 5 nanometer around 2 to 3, 2 to 5 nanometer. Okay, so the overlay distance will be really small. And once you replace the MOSFET with this CGD and SGS, what happens here is that we can look at what is the equivalent circuits that we can replace it with neither. Because the nearest one is too complicated to calculate because we want to separate the input and output side. So you can use the Miller effect to judge from a blank box. So if you have a system with two different voltages with certain Z coefficient, and you can use this way to separate the connection. So for instance, if your V2 over V1 is a function of K, and then you can divide this component into input and output part with the equivalent impedance. And this impedance is replaced by Z over 1 minus K, and then Z over 1 minus 1 over K. So you get a new impedance and both input and output side. So there's a typo, it should be V2. Okay. So other is the constant, you can judge how much impact on your capacitance. So you can think that we relocate the high frequency from this curve. Maybe I didn't draw it here, but I quickly draw it in the blackboard. So here is the signal input impedance, signal impedance, V signal. And then here's I try to transfer the capacitance to here. And this capacitance will be CGS. And also there will be a CGD. Plus the transconductance. CGS. Here is CGS. And then we have RDIL, the output equivalent resistance. And the CGD, here is the CGD multiplied with the 1 plus GN RB. are out. Okay. So actually, we can separate the capacitance into the part using the above Miller effect. This one I will not show you in the final. Maybe all of that's already been done. So there will be nothing regarding about final, but I still need you to understand. So we separate the capacitance, and you can see this capacitance is just like the RC type constant. So in order to calculate the high frequency response in your transistor, you need to separate this capacitor and the drive, how it impacts your high frequency response. So if you look ahead, I'm not sure if I show the slide here. Maybe there's no spatial slide. Anyway, so you can see that individually there will be still the same behind the CMU. So you get additional CMU, which is 1 plus GM ionoplug. Ionoplug is the output resistance. So you get a higher resistance, you get a lower frequency response. Okay. So you can see that how do we actually reduce the capacitance in between the transistor? You need to consider replacing with low-K material or even with the anode. Okay. Now, there will be additional things we want to cover, especially for drain-induced barrier loading. So you can consider we have the drain with higher voltage. And with higher voltage, we previously draw the band diagram pretty precisely with certain artificial angle. But that one doesn't exist in your transistor. Because when you have a higher drain voltage, that will give you the reduction of the drain needed drain voltage. So if you get a higher drain voltage, that will penetrate the certain channel and lowers the barrier. So you can consider previously we build up a channel, but if you get the drain region closer to the source, the barrier will be lower down, especially before you turn on the gate voltage. So we can consider we want to turn off the channel. How do we turn off the channel? It is P type and it is N type, N type. But under this constant, if you get a high drain current, everything without there's no current. So we turn on the gate drain voltage, there should be no current flowing through. But unfortunately, since your device is really tiny, only maybe 12 nanometer, you still get a certain current passing through. So that means you get leak current when you turn on the drain voltage. Okay. So you need to consider when we work on this small device, there will be some leaky current which is induced by the drain induced barrier lower. Okay. And also that will cause you the threshold voltage reduction because initially we get certain drain induced loading, and that will give you originally we judge the threshold voltage based on the metal oxide semiconductor process. But during that process, we assume it is a bulk material, get a really long channel. But once your channel is short and you get a voltage along the drain side, you lower the boundary between the source to drain, and then maybe that will give you certain leaky current. It is the basic. So you get certain leaky current increasement, especially the loading of the threshold because the subthreshold leakage current we used by this voltage. But there will be some degraded performance. So it is the main diagram to show. So you can consider that initially we have certain barrier. Here is the N-type semiconductor, P-type semiconductor, and N-type semiconductor. The baseline is without the drain voltage. Okay. So initially we do not have any current flowing through, even you slightly increase the drain voltage. But unfortunately, so here is the really long channel. So you increase the drain voltage. You can see even we increase the drain voltage, there's a gap between there's a boundary both at the source and drain side. So there's no current. But if your channel is strong, in comparison with that part, you still apply a really large drain voltage across the system without applying gate voltage. So we assume the channel still turned on. But the barrier will be lower. So instead of have still a high barrier, like the one without gate voltage, we get a certain drain induced barrier loading because the short channel. Okay, so we get the possibility that we get certainly barrier. because there's no barrier like the moving content. So you need to consider if your channel shift forward, how do we track the current? So why we can improve the performance of your transistor even without shifting the dimension? We can use like a feedback. So previously we just consider like a planar transistor to control the gate on the surface only, but there will be some leach current on the subject, and also there will be some bearing issue. But if you consider there will be a feedback, so we get the gate around the fin. So we control the three dimension of the service of the pin service or the T substrate. So we are able to easily turn on and turn off the transistor to start to get the extra big current. And what is the extremity case? What is the best case? We get a gate around. So your channel is like a round one, and we get the metal around it. So you are able to precisely control how much currents we can reduce from the channel. So that's people work on. I think about 10 nanometer technology, TSMC will be with that technology. And why people cannot work in like here with FinFET, I will talk about implementation in the next post statement. You can consider that why we change the structure of the transistor and how we improve the performance of your device. And also, I think maybe some of you are working with some technology like the 3.5 material and hand structures. And for hand structures, why we can improve the performance? You can think they use the EPO junction, and it could be the EPO junction, the beta icon could be in your meter. So the idea is that if you find two transistor, two different semiconductors like the GaN line and the VKN line, you can increase the carrier population or carrier density, trying to form a trap in between the EPO junction. Okay, so you can consider that by connecting with two N-type semiconductors, there will be a trap between the connection. And there will be certain discontinuity between the conduction band and the balance band. That's what we call the two-dimensional electron case. So what is the benefit of this one? So the previous case, we tried to use the doping, use the inversion layer to increase the carrier concentration. But here is as long as you can turn off the circuit, there will be naturally high density carrier, which we can improve your current. So instead of using high K or some fancy technology, we can try to get a really large population of the free carrier or like a carrier reservoir. And then so we can drive this two-dimensional case in order to get a high speed or I think people talk about the high power transistor. So this kind of device can be used as the two-dimensional high power transistor. So it is still based on the effect transistor, pure effect transistor, which is compatible with the 3.5 material, but typically the dimension of your wafer is smaller compared with 12-inch technology, 300 millimeter technology. So I think for 3.5 material, people working in our lab is only use like a 2-inch to 4-inch, maybe only in 2-inch because the epitaxy substrate is quite expensive. And then that will give you better conductivity for this EPO junction. I think so based on these advantages, you can say you can build out large electron density. So typically on the order of 10 to 12. A very big thing there, only within 10 nanometer, for example. And the electrons are confined with the EPO junction. And the only question is how do we turn the device? So there will be some so for the gate material here on the channel, you can not use a really high conductive layer. Okay, so if you are working with a really high conductive layer, what happens? You always have turn on behavior. So the only question is that how do we combine with the channel with a little bit lower conductivity together with the 2D material. And also, it will be pretty similar and analogous to a MOSFET. So you can get a higher mobility, maximum electron velocity in gas. So in comparison with the the ID here to be sure. Where is ID? Do I have an ID here? Camper. Okay. So what is camper? It's mu1 C outside. So if you replace the semiconductor from silicon to gallium arsenide, the mu1 will be larger. Okay, that's the key. So 10 times larger or 3 times larger for gallium arsenide. So you are able to get better response and also higher cutoff frequency. Okay. So that is some benefits in addition for this process. Okay. And that should be the last slide here. Okay. So I want to cover some logic circuit and also some application part. So as I mentioned, the gate MOSFET gives you certain benefits, especially if we not have any current. So we build up a trillion linear transistors with the MOSFET. Let us talk about why we call it MOSFET or CMOS technology. I think most of you heard about CMOS and why we call it CMOS. I think you already know MOSFET, they know as a semiconductor. But why we call it complementary? So here's we call it CMOS. FET. So we can replace this CMOS technology. Okay. So complementary means that we both have N and P connection. Okay. So for this N and P connection, we call the CMOS inverter first as an example. And of course, I heard some of you may work with microelectronics, so they work with memory or they work with the high density memory. And then both on the memory part and the inverter part, always we use both CMOS and PMOS. You can consider we take almost as an example with pin trend to build up N or electron channel. But this one just give you like an amplifier or logic operation 1 to 0. And why we want to combine with PMOS. So let us consider this part. So the general idea is that to typically connect both N type and the P type together as the circuit. Okay, so it is the most fundamental transistor or the inverter we will use. So you can consider here we get VDD. The only difference with the one we previously introduced is we replace the resistance here to be a PMOS transistor. So here's this NMOS, here's PMOS. Okay, and then here's we use both P and N MOSFET. So we call it complementary. Okay, and also in memory they also use like the NMOS and the PMOS together. So what you can simplify this technology to be 2 to each. That's the video game. You get 2 to each, better be output. Okay. So when you turn on one transistor, the other one will be turned on. Okay. So for instance, if you turn on this one, we get a VDD. When you turn on this one is off, so you get a high voltage. When you turn on this one is off, you get a low voltage. So you get a 1 and a 0 as the digit operation. So why we get this one is because when you input V in, it's 1 V. But then you are working with VDD or 5 volt for logic operations. What happens is that if you get a high voltage here, you get a almost up. But for PMOS, you get the same voltage of course in US. So there's no inversion channel. Okay. So if you are working with this one, you only almost up. Okay. And for these conditions, you can think that it is grounding. This one is total. because you get the same potential. And you get a voltage on to replace this one can be like RDSN, which is equals to mu NC outside. Maybe 1 over mu NC outside. Q over L VDD minus VD. Okay, so what we get here is that we assume how much current flow, okay, and how much voltage we can get, okay. So the voltage we supplied is just like a VDS, right? And this current equals to 1 over 2 mu NC outside multiplied with WL VGS. What is VGS? VDD. So we apply profile for VDD minus VT. Okay. So here's the current, and then you divide the current by VDS. So the RDS equals to 1 over QHD outside WL over L VDD minus VT. So you can try to say, okay, so this one equals to the 0 volt, which is the logic 0. Okay, maybe it almost equals to 0 volt because you think this one is a large number. So you get a small output voltage. And vice versa, if you get a 0 voltage here, that means you turn off the circuit on the button, you turn off the NMOS phase, you turn on the PMOS phase. And when you turn off the PMOS phase, there will be current flow. And then you get the voltage just like a minus VT to be here. Just like a VDD to be here. And then you get a high voltage response. Okay. So it is like a inverse operation, inverter. Okay. And how do we draw the corresponding figure? So let us look at the corresponding figure. If you consider the VGS equals to VDD, that means you turn off the bottom one, the NMOS on. So when you turn on, here's the NMOS code. You get the same output VX, or we call it V out. And here is ID. Or you can see how much current flowing through the system. Okay, so it is exactly the same curve we draw a lot of time here. But how about the other one? So for the other one, we consider the PMOS. From PMOS transistor, you can see here it is from the output is still from high, right? High voltage to how much current we get? Get almost 0 current. And from PMOS, we substitute the VDD from the above the high voltage. So here we get it is the up voltage VDD. Okay, so when we replace the resistance with the transistor, we need to draw both transistor ID curve, IDVG. Okay, so make sure you heard about IDVG. That is the regular curve we want to operate. And since we know it is the graphic solution, where is the operation point? Where is the operation point? That will be the crossover with each part. So you can say that will be here. Okay, so actually when we connect two transistors and we turn on the transistor on the button, instead of using the resistance, it is not in saturation region. It is in trial region. Okay, remember what I said before. If you want to work with logic circuit, we want to use the cutoff region and the trial region. In BJT mode, it will be cutoff region and the saturation region. Okay. So for these regions, we work the NMOS phase in trial region. So the current is still low, but what is the output voltage? Will be low voltage. Just like you have the high input, you turn on the transistor, but the current, since there will be still a low current here, So we get the voltage the same from here to here. And then here is the resistance from the trial region, right? So we try to solve the graphic solution. Here's the zero point based on this inverter. And then this is the steady state. So we can say here is the P mode transistor, which is off. And here's the N mode transistor, which is on. If VGS equals VDD. Okay. And how about the other one? Let's try to draw it again. If VGS is 0, so the input voltage is 0, what will happen? That was simple. On the bottom one, we get NMOS, which is cathode. Here is NMOS, which is O. Here is the still output voltage, IP. Okay. Now how about the PMOS one? If you work with low voltage, you turn on the VGS here with the reverse bias because it is PMOS. So you accumulate the positive pole along the channel. So when you have the channel get the IV curve. First you get rid of everything. Just say, okay, so VGS is up. So for PMOS, we get the curve like this. Like the inverse of your, here is the trial region, here is the subscription region, and then here is again it's VDD. So this one is PMOS, which is up. And since we operate with the graphic solution, which is the solution here, it is here. So corresponding to the current is still low current in trial region of PMOS. And what is the output voltage? It is almost at, here is the output as 0. And then here is output as 1. Okay, so that is the inverter we work with. So in comparison with the one pretty similar to the inverter, maybe back to the slide. Maybe you don't like that. Maybe this one. So you can see the regions we work on is like here and here. But this one is connected with just a resistance. So if you work with resistance, the voltage will be certain value. So there will be a certain not so perfect output. Okay. So that is the reason if you connect both NP transistors, you are able to improve your performance. So instead of you working the region at here, the previous one, how do we link the RD? So the previous one, here's the relation we use RD. So what happens here is maybe you work the region here, even it is low voltage, but you still have a certain voltage level like a 1 volt here. It is not a good thing because we want to maximize your I diagram, maximize your digit signal, get better separation. So if you replace RD by this curve, you can dramatically increase your performance. That is the power for CMOS operation. Okay. When you are working with CMOS, maybe you can draw a more complicated figure, just like it's not important here. Let me know, please. So you can start with certain value. So maybe give you a table and the corresponding the input voltage from the volt. Maybe we just consider VDD is 3 volts. So 1, 4. So maybe your input is from 0 to 3, maybe not to 5. Maybe the VDD is still 5 volts. So you get a certain VGS in NMOS, which is 0 volt, 1 volt, 2 volt, 3 volt. But for VGSP, it is a minus 5 volt, minus 4 if you use BTD as 5 volt, okay, so get a 3 volt. So if you draw the corresponding solution, like here is the output voltage, here is the IT. We first plot the NMOS state, the curve of NMOS state from 1 volt. Here's 3 volt, 0 volt. The white one is NMOS. Okay, so here is 2 volt, here is 3 volt. Right, that is the regular curve we plot with. And then for the corresponding PMOS. So here is PMOS. So we notice that we divide this one, like you use 0 volt, the corresponding USB will be minus 5 volt. It's just like use 0 and then you use 5 volt here. The difference between VGS will be negative 5. Okay, so for negative 5, that means you get really high high voltage here. It is maybe negative 5 volt for your PMOS. So you get a certain solution here. And then also you can find if you are working with the 1 volt, the VGS is 4 volt. That will give you something like here. So the second curve will cross over 1 volt here. So you get a solution from here, jump to here. And how about you use the 2 volt in VGS? You get a minus 3 volt. Here's minus 4. Here's minus 3. So the solution with this curve will jump from here to here. Okay, so you can always connect. So you can simply, what we do here, you separate the NMOS and the PMOS corresponding to the gate to source voltage. And by this corresponding, you plot the curve both for PMOS and the NMOS. And you can find the cross section, the crossover in graphic solution corresponding to 0 volt to minus 5 volt. You find the 0 volt in NMOS, minus 5 volt in PMOS. So you can draw the corresponding output voltage. Okay, so maybe consider this.